All right, so this should be D5, not C5. All right, so based on what we talked about in D4, I think D4 will help with this a lot. Figure out which of these is ionic, which one is network covalent, which one's molecular covalent, and which one is metallic. So we drew some pictures that look a little different in D4, but I think that'll help you figure out which is which. So for one of these, write ionic. For one of them, write network covalent. For one of them, write molecular covalent. And for one of them, write metallic. And look back at D4. There's some drawings in D4 that'll help you. All right, which one is ionic? Maddie. Number 2 is ionic. 2 is ionic because you can see the positive and negative ions arranged in a repeating pattern in a crystal lattice. So these are positive and negative ions. That's too big to be an electron. That's not an electron. That's a negative ion. That's a positive ion. Which one do you think is network covalent? Ashley, which one do you think is network covalent? Yep, number 1 is network covalent. Notice there's no ions in there. There's no positive or negative. It's just a bunch of atoms, and each line represents a covalent bond, okay? Today in D6, we're going to be drawing covalent bonds, and you'll learn how they're often represented by lines. So the lines represent electrons being shared. So this is a nice rigid network covalent structure, okay? These bonds are harder to break than these bonds. Covalent bonds are extra strong. These bonds are strong, but they can break. These are much harder to break. Which one is molecular covalent? Hayden, what do you think? Which one looks like molecules, like clumps of molecules? What? So this one's molecular covalent. Because you can see these separate discrete molecules. There's clumps of atoms bonded together, okay? And then number 3 is a metallic bond. So we drew a metallic bond in D4, and remember metallic bonds have a sea of electrons. These are delocalized electrons. I know it's hard to tell they're electrons because they're not labeled as negative, but they're negative. These positive cations lost their electrons, but they didn't have anywhere to go. There's no one to take the electrons from the metal. So the electrons just kind of move around from place to place. These are attracted to the positive cation. There's attraction here, but they're not stuck in place. This is not a rigid structure, okay? So that's why metals look different from salt or a diamond or something like that. It's a much less rigid structure because of the delocalized electrons. All right, so the state at room temperature, network covalent things. These are always solid at room temperature, okay? These are rocks and gemstones and diamonds. Ionic things are also always solid at room temperature. Ionic things are always solid. You will never see an ionic compound as a liquid or a gas at room temperature. Never, ever. It's always a solid. Metallic things are also always solid with what's the only metal that's not a solid at room temperature? Mercury. But with the exception of mercury, all metals are solids at room temperature. Molecular covalent is where we get some variety. These are solid, liquid, or gas. Okay? There's a lot of variety among the molecular covalent. But in general, if you see any type of compound that's a liquid or gas at room temperature, it's molecular covalent. Okay? Any compound that's a liquid or gas at room temperature is molecular covalent. And whether it's a solid, liquid, or gas, draw yourself that dotted line. Whether it's a solid, liquid, or gas at room temperature depends on the strength of that intermolecular force, okay? So again, because something seems kind of soft or liquidy or whatever, don't say, oh, it must have weak bonds. These bonds are just as strong as these bonds. Covalent bonds are super strong. This bond is strong, these bonds are strong. It's the intermolecular force that makes these soft, or makes them liquid, or makes them gas. It's the intermolecular force being kind of weak. Melting point. Okay, like you guys predicted in the Do Now, and you were correct, network covalent has the highest melting point, okay? Has anyone ever melted a rock? Or a diamond? No, right? Rocks melt when they're in the center of the earth, and you have molten rock or whatever, but very, very, very hard to melt a network covalent substance. You would actually have to like break that covalent bond. Ionic substances, they're not as high as that. I would say ionic substances have a very high melting point. Some ionic things will melt on a Bunsen burner, whereas the network covalent, I don't think we could ever get that to happen. But ionic things are very hard to melt. You'll notice the ionic things did not melt on the hot plate. But on a Bunsen burner, maybe. I think there's a lab later this year where we do melt an ionic substance on the Bunsen burner. I would say metallic is just high, okay? Metals do melt, okay? But they have to be pretty hot. And then molecular covalent tends to have the lower melting points. So the first things to melt on the hot plate were the molecular covalent things, the sugar and the wax.
What kind of bond is glass?
Glass, that's a really good question. Glass and sand are the same thing, right?
Yeah.
They're both silicon dioxide, which is the same thing as
That's
quartz.
what I was about to say.
Someone, I heard that glass is actually like a liquid.
Oh, wait, what?
Can I get back to you on this? Because I feel
Okay.
bad that I don't know the answer to this.
You say glass like a liquid? Wait, okay.
Some people say, because the structure of glass doesn't fit into any of these categories.
Oh, okay.
So glass actually fits more of a liquid structure,
Glass is fake.
but it's definitely a solid.
No, it's like 100%
It's
a
fake.
solid.
No, the glass is fake.
Okay, Tim.
I've heard that like glass is a liquid because like the old cathedrals and stuff, like the glass windows are much harder.
Yeah, it kind of like
Like
sinks a little bit. Yeah, I know that glass and sand are the same thing. There's silicon dioxide, which is also what quartz is. They just all have different structures. I'll look into that. I'll get back to you because I don't know. It has glass has covalent bonds because it's silicon and oxygen, but it's not molecular and it's not network. So I'll get back to you. That was a good question. All right, physical description. Network covalent. These things are crystalline, which means they have sharp edges and like straight sides. They don't dissolve, obviously. I didn't have you try to dissolve the rock in the lab because I think you knew it wouldn't dissolve. They also don't conduct. Okay, their electrons are locked in place in the covalent bond. Okay, so when you held the electrodes to the rock, it obviously did not conduct electricity. Okay, so some examples are diamonds, gemstones, rocks. Okay, so that's what you should picture when you hear network covalent. Okay, these don't react that much. This is really the last time we're ever going to talk about network covalent because these don't really do anything chemistry-wise. Okay, they're so locked in place. The electrons are where they are. Rigid structure kind of stays the way it is. Ionic things are also crystalline. They're a little more breakable crystalline. Picture salt. When you hear ionic compound, just picture salt, because most ionic compounds look like salt, even if they're not technically sodium chloride, okay? So it's crystalline, but you can make it more granular, or some ionic substances are even like powdery, like the baking soda was. But they do dissolve, okay? They do dissolve in water. The reason they dissolve is because they have positive and negative ions. The reason these dissolve is because they have positive and negative ions, and water is polar. Okay, what does it mean when we say water is polar? Someone who's in AP Bio. Huh? Polar things like water, but why is water polar? Yes, Hannah.
Positive and negative regions.
Yes, exactly. Water molecules have a positive end and a negative end. And so because water has like the North Pole and the South Pole, positive and negative end, because water has a positive and negative end, it's able to pull the ions off. So the positive end of water pulls the negative ion off, the negative end of water pulls the positive ion off. So this, when an ionic substance dissolves in water, the ions are literally being pulled apart from each other. So just water is able to break these ionic bonds. Okay, so they're not that strong if they can be pulled apart in water. Okay, so things that have positive and negatives tend to dissolve in water because water also has positive and negative ends. So that's why they do dissolve in water. They also conduct when dissolved or molten. Okay, so the ionic substance conducted when it was dissolved in water. You put the electrodes in, it carried a current. We didn't melt the ionic compound, but if we had melted it and had a really, really hot Bunsen burner and be able to melt it and put the electrodes in, it would also conduct when it's melted. Did it conduct as a solid, though? When you put the electrodes in the salt, did it conduct? No, okay. When it's a solid, the ions are locked in place. They're not going to carry a current. But when it's dissolved, can they move around? Yes. When it's melted, can they move around? Yes. And all you need to get an electrical current flowing is moving charges. So if these are in a situation where they can move, they can conduct electricity. But as a solid, they're not going to conduct. Only when they're dissolved or molten, okay? Molten's the word we use for like the liquid form of something that's a solid at room temperature. So like molten rock. Rock is normally a solid, but when it's a liquid, we say molten. Molten salt. Salt is normally a solid, but when it's melted, we say molten. Would you say molten water? No, okay, because water is already a liquid, okay? It's kind of like the word vapor. We don't say oxygen vapor because oxygen's always a gas. We don't say carbon dioxide vapor, but we say like water vapor because water's normally a liquid and a vapor is used to describe the gas form of something that's normally a liquid. What were the ionic substances in the lab, everyone? Salt and what was the other one's common name? You remember the common name for the other ionic compound?
Oh, is it baking soda?
Baking soda.
Yeah, that was.
I know baking soda doesn't look as crystalline as like the salt. It's more like ground up into a powder form, but some ionic compounds look like that. Some of them are kind of powdery. So when these were dissolved in water, they conducted electricity because the ions broke apart and were able to move around and carry the current. All right, metallic things tend to be a little bit more soft. Not all metals, but they're softer than, say, like a diamond. Soft, malleable, which means you can shape them. Ductile, which means you can draw them into a wire. Shiny. All these things make it very different from these other types of substances, okay? I know like iron is pretty rigid, but you can still shape iron and bend it into things and you can do things with it that you can't do with like a diamond or a rock or salt, okay? And some metals are really, really soft. Like the alkali metals, you can cut the alkali metals with a butter knife. You've just never seen them because they're so reactive, but you can cut them with a butter knife. They're very, very soft. Whereas over here, they tend to get a little bit more, they get much more rigid. These lose, like each of these atoms loses like 2 or 3 or 4 electrons. So these have a lot of delocalized electrons because they're losing 2, 3, or 4 valence electrons, whereas these only lose 1 valence electron. So there's not as many delocalized electrons kind of gluing it together, whereas over here you have a lot of delocalized electrons helping, make these metals a lot more firm. What else? They also conduct electricity and heat. And again, that's because of the delocalized electrons. So even in solid form, the electrons are mobile. Okay, even in solid form, the electrons are mobile. And having moving charges is how electricity flows. You need those charged particles that can move. And that's how the electricity flows through metal. So examples of metal, aluminum, you're all familiar with. Lithium, you've probably never seen lithium metal because it's super dangerous. But you can cut that with a butter knife. Then we have the ones from the do now, the ones that are mixtures of metal, things like steel, bronze, brass. What's the word for these from your reading? Starts with an A. Alloys. Okay? Alloys. Alloys are mixtures of metals. Okay, alloys are mixtures of metals. We don't really call them compounds because there's not a fixed ratio. Like steel is mostly iron with some carbon mixed in, but there's not a fixed ratio. So it's not really a compound with a chemical formula. It's more of a mixture, but those things in the mixture are all metallically bonded to each other. So steel is mostly iron. Why wouldn't you want to build a building out of iron? What's it going to do? Rust, okay? So when they learned to make steel about, I don't know, 150, when did they learn to make steel? 150 years ago? Industrial Revolution, right? I don't know, the Steel Age. When they realized that the reason they make an alloy is because it improves the properties of the metal. So iron rusts, but there's a lot of iron out there. But they realized if they melted the iron down, mixed in some carbon, and then refroze it, it wouldn't rust anymore. So usually when they make an alloy, they're improving the properties in some way. And then once we had steel, we could build skyscrapers because, we knew it wouldn't rust. And, you can build things much taller when you know that they're not going to rust. Molecular covalent. Did these dissolve? Did the wax dissolve? No. Did the sugar dissolve? Yes. Okay. So the thing with molecular covalent is that some of them dissolve in water and some of them don't. Okay. Some dissolve. Some don't. So you can't tell if something's molecular covalent or not just by whether or not it dissolves, because sometimes some of them dissolve and some of them don't. Which ones dissolve in water, the polar ones or the non-polar ones? Polar substances dissolve in polar dissolves in polar. So water's polar, so polar things will dissolve. Sugar is polar, that's why it dissolves. Wax is non-polar. Okay, it doesn't dissolve. The words you learned for the polar and non-polar in biology were hydrophobic and hydrophilic. Does that sound familiar? Yeah. Same thing, okay? So wax is non-polar. Is that hydrophobic or hydrophilic? Hydrophobic, right? Wax is hydrophobic. It's non-polar. Sugar is hydrophilic. It's polar, okay? So same reason as we have up here. This dissolves because of the positives and negatives. If these molecules have a positive end and a negative end, you could see how the water molecules can latch on and pull it into the solution. Whereas if these molecules don't have a positive and negative and they just kind of sit together in a clump, the way that wax or oil would, wax and oil, grease, all those things are non-polar. They just stay together. They're not pulled apart into the water. And later on this year, we'll learn how to tell if a molecule is polar or not. But we're not going to get that far yet. All you got to know now is that some molecular covalent dissolve, some doesn't. And they don't conduct. Okay. So the molecular, even if they do dissolve, it still won't conduct electricity. Okay, there's no charged particles. When these dissolve, the entire molecule gets pulled into the water. There's no separate ions around or separate electrons around. The whole molecule is getting dissolved. There's no charged particles floating around. So the molecular covalent things from the lab, you had sugar, you had wax, some other things just in our everyday life. Oil is molecular covalent, water is molecular covalent, CO2 is molecular covalent. So you see there's a huge variety. Sugar, carbon dioxide, very different things, okay? Huge variety. And the variety is due to the difference in that intermolecular attraction. For sugar, the intermolecular attraction is very strong. Carbon dioxide intermolecular attraction is almost non-existent, okay? Also, all biological molecules. What are they called? I don't know anything about biology.
Oh, I know that.
Macromolecules?
Yep.
Yeah. I actually don't.
All right, your biological macromolecules. What are they?
Proteins, lipids, carbohydrates, and fats. Right?
Got it.
You said
Nucleic acids.
Nucleic acids.
All right, so like this right here, these things that you're used to seeing in biology, these are all molecular covalent. They're called macromolecules because pretty large molecules. Living things need a lot of complex types of molecules in order to be alive. So molecules in living things tend to be very complicated. So even though they're big, they're still molecular covalent. Each line represents electrons being shared. Okay? So all the biological molecules that you learned about were all molecular covalent. All right, so let's move on to D6. Next page. Moving right along. Cross out C6. I don't know what I was thinking. And write D6. Get out contrasting color. My favorite thing. If you have it.
Are we doing all of D6? We just start.
We're doing the first page and part of the second page. All right. So what we're going to do in D6 is draw Lewis structures for covalent. Okay, we've already done Lewis structures for ionic. Electrons were transferred. We drew an arrow. We drew the dots and then we drew an arrow. In covalent, electrons aren't transferred. They're what? Shared. Okay. So now we're going to learn how to draw a Lewis structure where electrons are shared rather than transferred. Okay. These can get kind of tricky, okay, because some of these molecules can get very big and very complicated. For the more simple molecules, I got two methods for drawing these types of Lewis structures. That's a lot more difficult than ionic. First method I made up, I call this the jigsaw puzzle method, okay? All you do with this method is you draw the central atom with its valence electrons, okay? The central atom's whatever you have the least of. What do we have less of, N or H? N. Draw that in the middle with its valence electrons. And then place the outer atoms where they fit, okay? N needs 8 valence electrons to be stable. So we're going to see that one's going to latch on here, one of the H's will latch on here, and one of the H's will latch on here. How many valence electrons does H bring with it? 1, okay? So each draw, with your other color, draw an H, bringing 1 electron. Draw an H, bringing 1 electron. Draw an H, bringing 1 electron. Okay, and you can see by sharing, nitrogen was able to achieve a full octet. So draw a circle around nitrogen's octet. Now the nitrogen is stable by sharing. And remember, the hydrogens are the exception. They only need 2 to be stable. Hydrogen only has 1 energy level. So hydrogen is full with 2, whereas all the other nonmetals are full with 8. So the hydrogen is now stable, hydrogen is stable, hydrogen is stable. And so you can just kind of see how they fit together. Okay, so for the structural formula, it's a lot like the Lewis structure, except we draw the bonds as lines instead of dots. Oh, wait, I forgot this. This right here is a single bond. Did you learn that in biology? 2 electrons is a single bond, right? Okay, so when they're sharing 2 electrons, that's a single bond. We get really sick of drawing the dots. So in the structural formula, you just draw the single bond as a line instead of dots. So that's a single bond to H, single bond H, single bond H. And just in your mind, when you see the line, you know that that's 2 electrons being shared. 2 electrons being shared, 2 electrons being shared. The lone pair, the unbonded pair, has to stay as dots. Okay, you still have to keep that. Okay, and we call that a lone pair or an unbonded pair. And those play a bigger role in the shape of the molecule than you might think. So you do have to draw those. But it just goes quicker drawing the bonds as lines instead of dots. All right, Br2. Draw yourself a Br with 7 valence electrons, like that. And then you can see where the other Br is going to latch on. Okay, the side that has 1 missing is where the other Br is going to come in, and it has 7. 1 to share, and then the other ones on the other 3 sides. Like that. Okay, and then just draw a circle around each octet. And then as again, this is a single bond, so when you do this, just draw it as a line. And then keep the lone pairs, okay? And just know in your mind that that line in there is 2 electrons being shared. Okay. Next one, CCl4. Which one's going to be the central atom, C or Cl? C. Whatever you have the least of is in the middle. Give it, and carbon has 4 valence electrons. Okay, so go ahead and draw the 4 Cls. It's pretty clear. You can see where the Cls are going to latch on. Okay, so you can see Cl has 7, one that's going to share, and then the other ones it'll keep for itself. Cl, 1 to share, a bunch for itself, Cl, 1 to share, and Cl, 1 to share, like that. Okay, and then put circles around all the octets. Full octet, full octet. So these electrons that are being shared count for carbon's octet, and they also count for chlorine's octet. And then for the structural formula, you can just do it as lines. Each single bond is a line. And then keep the lone pairs on the chlorines. Okay, try N2. Okay, next one is N2. Try that one. Does it work? No. Okay, see how hard it is to get, okay, you got this, then you're like, okay, well, I'll bring this nitrogen here to latch on, but it just doesn't work out, okay? It will work out eventually, but just don't use this method, okay? When that happens, if you can't immediately see how it's going to jigsaw together, just give up and use method 2, okay? So, method 1, write yourself a note. Method 1 doesn't work. Okay, if you can't immediately picture how it's going to latch together, method 1's not going to work. Okay, use method 2. Okay, use method 2. So when method 1 doesn't work, just stop and use method 2. Okay, so flip over to the back. Method 2 I also made up myself. Called, method 2 doesn't have a name other than just method 2.
Called if method 1.
Yeah, tell me what the name should be after I teach you how to do it, because I can't think of what to do. All right, method 2, if method 1 doesn't work. I'm actually not going to have you do N2 yet, just because that's a pretty complicated one, but we're going to do O2. O2 has the same issue that N2 has, okay? O2 has 6 valence electrons. Bringing in another O is not going to solve the problem, okay? So what we're going to do is draw the skeleton structure without dots. That's the key. Draw the elements. We're going to have 2 O's next to each other, but don't give them any electrons. Don't give them any electrons. Now you're going to add up all the valence electrons on the side. So we're kind of pooling all the valence electrons together. This is going to have 6. This is going to have 6. Write this down. 6 plus 6 equals 12. Okay, 6 plus 6 equals 12. Write that down even though it's an easy problem. This has 6 electrons. This has 6 valence electrons. We have 12 valence electrons to work with. So instead of giving this 6 and this 6 and trying to figure it out, we're going to place our electrons deliberately to make it work by following these steps. Step 3, make single bonds. How many electrons are in a single bond? How many electrons are in a single bond? 2, like that. So just put single bonds in between all the atoms because you know they need at least a single bond. Again, I don't care which atom these came from. I'm just using 2 out of the 12. Then fill the octets of the outer atoms in pairs. Okay, we're filling the outer atoms in pairs. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Put a check under the 12. We used up all 12. Notice I'm not specifying which ones came from this oxygen and which ones came from this oxygen. We're just pulling them all together and distributing. Now, is that structure stable? No, okay? If we had more electrons, we'd fill the octet of the central atom. We don't have any more electrons, though. So if you don't have enough electrons, step 6, make double or triple bonds by moving some of the outer atom's electrons. Go to the one that has enough. This guy has enough. Cross out 2. And draw an arrow. You're going to move them to the middle, like that. Okay, be sure you draw the arrow so you know where those came from. So the one that had enough has to share more than it's sharing. So now this one still has 8, but now this one has 8 as well. Okay, so go all the way over like that. That has 8. Go all the way over like that. So those 4 in the middle count for this oxygen, and all 4 count for this oxygen. Is that a single bond? No, that's a what? Double bond. So instead of drawing one line, we're going to draw 2 lines. That's not 0 equals 0. That's O double bonded to O. And then it looks a little funny to have these here and nothing up here. Electrons repel each other. These pairs want to get as far apart as possible. So with 4 electrons kind of concentrated in the middle, these pairs are going to go on the corners like that and like that. So they can get a full 120 degrees away from each other now. So by having so many in the middle, the ones on the outside can kind of like spread out a little more, if that makes sense. Okay. All right, CO2, what do you think is going to be in the middle? 2. Did you say 2? Which one's going to be in the middle, C or O? C.
Yeah, you did 6.
And then put an O on either side. All right, add up your electrons. Oxygen has 6, carbon has 4, oxygen has 6, for a total of 16. All right, the first thing we do is we make single bonds. There has to be a single bond there. There has to be a single bond there. What do I fill next, the central or the outer? Outer, and then central. Always start with outer, and then if you have some left, fill central. So start with the outer. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Put a check mark. We used up all 16. Is that carbon stable? No. So look at the atoms that have enough and move some more electrons to the middle. Cross these out, move them to the middle. Okay? So this oxygen still has 8. Now the carbon has 6 instead of 4. Now, do you think you're going to do it again on this side, or should we go to the other side? Go to the other side. Don't overload one side and make the side do nothing. Be symmetrical about it. Take 2 of these, move them to the middle. Now does the carbon have 8? Yep, and the oxygen still has 8, and this oxygen still has 8. So the way carbon dioxide looks is C double bond O, double bond O. And these lone pairs are going to swing out to the corners again, because they can now get 120 degrees apart, so they will. Okay. So that's how method 2 works. Okay, this would be very hard to figure out with method 1. It just doesn't jigsaw together. But method 2, what would you call this method, Reese?
Just because it works.
Just because it
Literally
works?
all I
used to call it the pool method. Like you pool all the electrons together. I don't know. All right, we'll pick this up tomorrow.
Oh, I got nothing else. I got nothing else. A lot of initials.